Projecting an image into a scruffy room corner leads to geometrical distortions. Due to the interaction of projected light and the underlying surface, colors are modulated as well. A precise mapping of projector and camera pixels can be derived by employing a camera in combination with structured light range scanning. This is used to pre-distort projected imagery so that it appears geometrically correct from the camera's perspective. The reflected radiance of a diffuse surface is given by all incident and projected light, modulated by the surface pigments. A radiometric compensation can be performed by solving the equation with respect to the projection pattern. Eventually, the synthesized image appears as if projected on a planar white canvas, although this is physically not present. However, the light projected by a single display pixel often bounces back and forth several times before it reaches the imaging sensor. Due to interreflections, refractions, scattering, and other global illumination effects, it may contribute to several spatially distant portions of the camera image. Assuming a direct mapping usually only considers the contribution with the highest intensity, thus discarding all global illumination effects. In some cases, it might not even be possible to acquire a direct mapping at all. The light modulation of an arbitrary scene is conveyed by the relation of the incoming and outgoing light field. These are four-dimensional functions that describe the incident and excident radiance on every point on a bounding surface in all directions. By employing a projector and a camera, a 4D slice of the full 8D reflectance field, including all global illumination effects, can be captured. This is done by displaying each projector pixel and capturing its contribution to the entire camera image. The acquisition can be accelerated by simultaneously displaying all pixels that do not contribute to the same camera pixel. The goal is to compute a pattern that, when projected onto a scene, results in a desired image from the camera's point of view. The relation between the incoming and outgoing light field, regardless of the scene, can be described as a transport function T. Its discrete form is a matrix that includes the contribution of each projector pixel to every camera pixel. Forward light transport has recently been used for BRDF and BSSRDF acquisition, relighting, and environment matting applications. An efficient hierarchical light transport acquisition scheme was described by Sen et al. In their dual photography paper. The left image shows the projected pattern and the right the camera image. High dynamic range imaging techniques are used to accurately measure irradiance on the camera sensor. The well-known equation describing the forward light transport is idealized by assuming that differences in the spectral sensitivities of cameras and projectors are negligible. In a real-world setup, this is generally not the case, because when displaying red light with a projector, the camera's green and blue channels are affected as well. Taking this into account requires the capturing of a light transport matrix for each projector channel with 3 colors each. By replacing the camera image with the desired picture, a simple linear equation system can be solved with respect to the projector pattern. When describing a direct relation of a projector and camera pixel, each matrix would reduce to a scalar. Only in this case is the coefficient matrix reduced to the previously employed color mixing matrix. An extension for general setups with R cameras and K projectors can easily be derived. This allows the full 8D reflectance field to be sampled. Global illumination effects such as interreflections occur whenever a single projector pixel affects multiple spatially distant regions in a camera space, or vice versa. A dual image, showing the scene from the projector's point of view, illuminated by the camera, can be synthesized by transposing the matrix. Typical systems with a camera resolution of 640 by 480 and a projector resolution of 1024 by 768 result in huge equation systems that may be impractical to solve. For a more practical application, the matrix can be decomposed into clusters of mutually influencing camera and projector pixels. Neighboring projector pixels are likely to overlap in the camera image. This may be a result of defocus, camera lens imperfections, or blooming, resulting in only a few or a single cluster in the transport matrix. Usually, it is desirable to split local connections while preserving spatially distant illumination contributions. In order to separate local from global light effects, all projector pixels affecting a single camera pixel are grouped into blocks of spatially neighboring pixels. The amount of projector pixels that can contribute to a specific camera pixel is restricted per block. It is straightforward to filter out lower luminance values in each block. Once the clusters are cut, a compensation can be performed separately for each cluster. An increasing neighborhood size is likely to produce smaller and more frequent clusters at the expense of discarding the interaction of close projector pixels as seen in this example. A diffuse surface is likely to produce very small and localized clusters, while interreflections and other global illumination effects will not. The images show decomposed clusters of the sample scene. Clusters are encoded in the same colors in camera and projector space. Performing the radiometric compensation for an input image as seen on the right allows a compensation image to be synthesized as depicted on the left. An optimal solution is provided by iterative non-negative least squares approaches, since projectors cannot display negative light. Projecting the compensation image onto the scene results in a corrected view from the camera's perspective. Highly refractive materials such as glass are a challenge for structured light range scanning because a direct mapping between camera and projector is not given. The acquired light transport matrix shows characteristic features that indicate global illumination effects. Missing portions within a region of the matrix represents the thicker part of the glass's rim. The twisted narrow bands illustrate refractions and the isolated portion being the glass's base that is visible only due to the refractions. Projecting a picture onto the scene leads to geometrical distortions and color modulations, which can be compensated. This scene includes interreflections and diffuse scattering. The left cardboard piece is coated with a self-adhesive transparent film. Projecting a colored pattern into the corners leads to increased brightness and color modulation of neighboring surface patches. These effects can be compensated. The difference is visualized on the right side. The light transport matrix was not decomposed for this experiment. These pictures show an uncompensated and a compensated projection of an image. Capturing projected pictures with a defocused projector camera system leads to a blurred image. Previous approaches applied a sharpening operator on the input images, which resulted in an enhanced perceived focus. Since projector and camera defocus is included in the captured light transport, a radiometric compensation optimizes the sharpness. Computing a single compensation image could take seconds or minutes depending on the size of the clusters. This does not allow a display of interactive content such as movies. However, the equation systems can be reformulated to enable an efficient implementation on programmable graphics hardware. Applying the light transport matrix's pseudo-inverse includes a computationally expensive pre-processing step and a matrix vector multiplication that can be performed separately for each projector pixel. Only non-zero matrix elements are taken into account and all necessary data structures are packed into optimized floating point textures. A comparison of the compensated image on the CPU and on the GPU using the inverse light transport shows marginal differences. These images show the light transport of the glass scene, its inverse and the composition images of both. Projecting the inverse composition would theoretically lead to a uniformly white camera image. This scene shows a compensation with the inverse light transport. About 30 frames per second can be achieved on a GeForce 7900 GTX with 512 megabytes.